Yep.
Right. And let me get that into the big screen. Why is that not going? Come on. Ah, there we are. Fine. Okay. I'll skip quite a few slides out of this, just give you the flavor of what it's about, right? EDR really started out from this problem. A lot of data is much too big to move around and easily copy and give people copies of. And the idea is that actually what you want to do is you leave open the crate and you take out the bit you want. And so that's what I call the big crate problem. And certainly for meteorology, with weather forecasts and climate, it really is big data. You really can't move it, right? You know, the speed of light gets in the way. And associated with this is what I call the biscuit tin problem, which is the metadata, right? The metadata you can squeeze into a small container and you can copy the containers around the world and they all point back to your great big crate and they tell you where the data is. And that's a completely different talk. But let's assuming that problem solved, you've got the data, but actually you don't want that great big crate. What you want is you want nice, convenient little bits of data that's just what you want, and you can go straight to it immediately and pick out what you want, right? So end of the pretty pictures. And the other thing that kind of fueled this in a way is when we started using the geospatial standards and maps, and meteorology had been doing their own maps for 150 years. And we're outside the geospatial community, and the geospatial community have got maps and layers. And as soon as we start using layers, we kind of break the paradigm, because typically a forecaster or climatologist or research scientist would look at data at perhaps 10 levels in the atmosphere for 10 times in the future or in the past. That's 100 layers. Can you choose that from a menu on a web map service? Probably a bit marginal, but once you've got 100 levels, which is what most models have nowadays, and 100 times, and hundreds of parameters, and lots of different versions, you've got millions of layers. The layer problem doesn't work. We try to use WCS, which is an OGC standard, coverages for getting fields of data. Didn't work, doesn't scale to thousands of users. So that's why we invented EDR API. Now the web coverage service, which is an existing standard, allows you to take a big multi-dimensional cube of data and trim it, chop away the edges, or take out a slice in whichever direction you want, or resample it and at lower resolution. But they're all kind of heavyweight, and it certainly didn't scale for meteorological users in terms of lots of users for a large amount of data. So we said, well, actually, most users don't want a great big chunk of data. They just want, what's the temperature tomorrow? What's the wind speed day after tomorrow at 25 meters above the surface, because I'm going to run a tower crane, and that will give me the wind speed. And what was the temperature? What was the wind speed 2 months ago when my chimney fell down in a storm and I want to claim on insurance? All that kind of stuff. There's loads and loads of use, thousands of use cases, and lots of people have been doing this in the various national Met services, allowing people to retrieve a single point from the great big mass of data in the crate, or collections of points, and that's what the EDR allows you to do. First simple query, position. Position meaning X, Y, Z, and time. Most of the geospatial people think of X and Y, and vertical and time are kind of second thoughts. We want X, Y, Z, and T first class. And of course, you can have time series at the point over the last year or whatever. The other patterns for a point is give me all the data above the point, right? A range, vertical range. Doesn't have to go the full depth of the atmosphere or full depth of the ocean or full depth of the lake or the full depth of a bit of ground. And you can have a time series of a profile. That's kind of a two-dimensional data structure. They're the position queries. More familiar area queries, give me all the data in the area. Give me all the data in a tile, which is just a rectangular area. And the bit that's relatively novel is I've got a trajectory going across space and time. Please give me all the data along that trajectory, which is exactly what the kind of thing you need for forecasting for aircraft or an underwater drone, all sorts of possibilities. Right? And of course, you can do 2D, 3D, or 4D. And a corridor is just a fat trajectory. because aircraft don't fly along exact trajectories, they fly down a corridor, so they can move sideways and up and down a little bit. So they avoid turbulence or whatever, so corridors are quite useful. Right. So those are the basic queries. That is EDR API. We'll skip all the history of why we're doing it. I don't think there's anything else worth saying anything. Lots of people interested. They're the charter members who are keen. We've done all the work. That's it. Okay.
Perfect. Thank you.
And the real important thing now is pass it back to you and let the guys show them it in practice. Oh, any questions?
Yeah, can you talk very briefly about the OGC process and where it's at?
Yeah, okay, the OGC process is standard working group produces a draft. It goes to comments of various people. When they feel confident, it goes to the architecture board, of which Dave is a member. They review it for quality. We passed that review earlier this year. We then went out for public comment on the draft, bit equivalent to the W3C process of first public working draft. We only had 4 comments, but at least it proved somebody read it. And then we are going to have a vote tomorrow to release it as a full standard. And that will happen tomorrow in the full technical committee. The process after that is on Monday, providing nobody objects or we pass the vote. Tomorrow, on Monday, the planning committee will then hopefully endorse that vote, and then it becomes a full OGC international standard.
Perfect. So I
could show that on the slide if you want, but I just want to skip all the text slides.
We are 98% of the way to the full standard, which is good.
No, it's better than that. It's better than that, Dave, because we've been working for a year, haven't we? We've been working for a year, and we're only 3 days away. That's 1%.
All right. So thank you. We'll turn it over to Mark here. Carry it away, Mark.
Right, thank you for that. This is a concept demonstrator that I've built to actually show how EDR will work in sort of the real world. I think one of the things that probably didn't come across in the previous slides was the fact that the idea is you shouldn't worry about the underlying data at all. It's not just talking big data. The idea is the EDR abstracts the underlying data structures from the consumer of the API. Another thing it does is breaks these queries up, as Chris said, into a set of predefined query patterns, which offer a fixed and limited functionality, and that allows a lot more freedom for implementers to actually optimize the back end and secure it, and offer different SLAs depending on the type of queries that the various users are consuming. This demonstrator I've got here is actually dynamically generating its query based on the metadata that's returned. And if I have a look at the metadata on here, give it a second. We work on a principle of 2 levels of metadata within the EDR API. There's this column metadata, the sort of information that a consumer of the API would require to actually generate a query to return data. And that is the basic core information that is needed to actually generate the query parameters and populate them and identify the ranges of possible values that can be passed into those query parameters. And you see here that this is the JSON returned, which actually gives all the information. And this information on the right-hand side of the screen is actually dynamically populated by the information that's returned in the metadata. And that's kept relatively simple. As I say, it's designed such that if you're a non-expert, and this is what this API is really targeted at, the existing OGC APIs are really offering powerful query interfaces to expert users. EDR is targeted at people who aren't experts on the underlying data. They are people who are interested in the information that's available from those data sources, but that's just one of the things they want to feed into their particular data problem. And ideally, the concept is EDR would sort of be on multiple different types of data. So you could pull in data from various different sort of providers with different sort of types of information provided. And in this demo, I've got meteor observations as observed site-specific data. I have a global gridded population density, which of course won't have any temporal information. That's just spatial, and it's two-dimensional spatial. I've got terrain information, and I've got global forecast data here in the form of GFS data. So here you've got sort of very different sources, but to the consumer, it all looks the same. What they see is an EDR endpoint described by this sort of metadata. And of course, by having those different types of data, we still want to provide users information about how that data was generated and where it comes from. And we do that in something that I sort of describe here as design time, as opposed to the runtime metadata required to construct data queries. You have design time metadata in the form of the links groups, which people can follow out to actually get further information about the data they're working with. This information is intended to be sort of something a human will go and look at when they're interested in building data APIs, rather than being machinable to actually generate the queries. And if I go back to the map, I can do a area query for the meteor data, which is point observations course, and pull in data. Now this map tool is completely generic. It's designed to actually parse the responses from EDR endpoints. So this one is the point observation data set. I pick a time range and get the data. At the bottom here, you can sort of see the URL that's been generated, and this is the query type, and then you've got something here that defines the area of interest using the well-known text protocol. And what I've got here is a set of point locations, because that's what's the underlying data. If I switch to a gridded data, the way I construct the query is identical. But the underlying data, of course, is very different. It's a gridded data set, it's bulk, but as a consumer, I don't know that. I know that the provider is providing information and providing certain query capabilities. In this case, the provider is providing a position, a radius, and an area query. Of course, those are all described within the underlying runtime metadata. So I can construct a query and get some data back. Actually, I'll construct a bigger area. Sorry, I selected a query without, I passed a query without actually selecting any data. I have done that now. So now you can see. Now, it doesn't look very interesting. Unfortunately, I've got a small screen here because it's a generic viewer. It doesn't have any intelligence about what to do with the data apart from using it does a dynamic scale based on the range of data available. Because it's a generic client, it's not doing anything interesting, but I've got a time range. I can see different sort of time levels. But it's exactly the same query pattern as was used for the point observation data that was coming from the Meteor. From the user point of view, they construct the query in the same way and the data comes back in the same format. There's just a lot more of it. And again, you've got the same for terrain and sort of population. But the whole idea here is you can dynamically generate a query based on the information in the metadata, and all the information you require to construct that query is available from the metadata from the API itself. It doesn't expect any knowledge apart from what it describes itself. And I think that's about the end of my demo there, Dave.
Perfect. Thank you, Mark. That's great. And we were going to move on to, I believe, Lei Hu, who should be presenter now. Make presenter. Yes. And if you all can't tell, this is a group that's done this demo a few times. It's great. These are awesome. All right, we see your screen. Take it away.
All right. So thanks for having me here. And so actually I made a demo video. I will just play it with my commentary. And so basically the demo contains two parts. So first is the implementation of our EDR service. And another is how we use that service in our system prototype. So because the system is deployed in the inner network, so that's why I didn't use the live show. So here is the main page. As you can see, it's based on the Pygeoapi framework, and it's follow the EDR API standard. So we can view the collections. So what we have here is the population, so which is downloaded from the WordPub website, and the village, the hospital, and the school, and bridge and paddy field data, which is from the Department of Emergency Management of Hainan Province. So let's move on to the example of the population collection. So here are some metadata. We can see that outperform it in special text, etc. And so the most important implementation is the query. So currently we support the position query, the aerial query, the trajectory query, and the corridor query. So let's click the position query first. So as you can see here, and you can click one point, and you have the WKT point and get data. They send the request, and you can get the population density back. Also the area query. You can draw an area. So it will have the WKT as a polygon, and click the population and get the population density data back of this area. And also the trajectory query. You can draw a trajectory here. And click get data. And we have the data back at the point. And last one is the corridor query. So similarly, you also draw a trajectory in the corridor, which is a fat trajectory, and you can set the corridor wise. So here we set like 800 meters. Get data. So here is the result of the data. So another example is the village. And also you can see some metadata here, and we support the aerial query of the village. So you can select the area. So this is the result of the village in this area. Similarly, the bridge. So this is a bridge in this area we drawed. So this is what we have done about the EDR service. So another work is how we use that in our prototype. So this is the application system. It's called the remote sensing disaster decision support system, which is deployed in Hainan province. So this system is used for the emergency response and impact assessment for the typhoon and flood disasters. So you can see this is the location of Hainan province. And here is an example of typhoon called Dianmu. And you could see the typhoon path and the rainfall distribution. So what we want is to calculate the impacted area and the impacted population once you click any typhoon checkpoint. So here we invoke the EDR service I just showed and query the impacted population. So another example is we want to query the impacted bridge, school, and paddy field, etc., based on the inundation area. So previously, what we use is the WPS service to implement it, but now we can also use the EDR service. So I think it shows the feasibility and advantages in our scenario. Yeah. So we just invoke this service. So we can see that this is a query result based on the EDR service. And this is the report that we generated at the last. So I think that's all for our demo. Thanks.
Yeah, no, thank you. That's excellent. I really like how that demonstrates the applicability of this to OGC API features, in particular with the sampling bridges and townships. Really great demo. Thank you.
Thank you.
Next up, I will, Steve, you were gonna speak, and I guess Shane was gonna be presenter.
Hey, Dave, I had to step away.
Okay.
So I'm just gonna go ahead and get started. Hopefully he gets back before I'm finished. So yeah, I'm just gonna go over our implementation of the EDR API. I'm Shane Mill from NOAA. So to get started, we developed a search engine. We really want to tie a user directly to the point of making a query. That was something we identified in one of the EDR API sprints, that there could be a disconnect right now to tying a user directly to the data. So let me just demonstrate that right now. So if I search for isobaric temperature for the GFS and click submit, this is just a prototype of a search engine. It's a little messy right now, but each result provides 2 links. Let me just show the second link really quickly. This is a CSW record that this search engine operates on. So this was just a prototype. One thing that we all agreed on within the EDR API, we want to move a little bit away from CSW and move towards OGC API records. So that's something that we have for future work to really drive a search engine and metadata aspects, is to use OGC API records. So let me get out of the CSW record. And then this takes you right to the point of making a query. So this collection is basically a collection containing isobaric weather parameters, and I had searched for temperature. So here we have temperature. I'm just going to demonstrate one of the feature geometry types. Here we have a cube. So you select a bounding box, you select temperature, you can select the time range, and then you can select the isobaric level range that you would like to see. If I click at data, you'll see the data return here. You'll notice this user interface is very similar to Mark's. The purpose of this interface really is just to show the coverage JSON output in a visual form. So that the UI is really just a coverage JSON reader. You can see that you can go through each of the times and the different vertical levels that you selected. Let me just go ahead and show an area query as well. Right now, our area query allows you to select one Z coordinate. Obviously, you can have more than one, but right now that's what we provide here. So again, a time range. And you can see an area query gives you a little bit more flexibility, more than a bounding box. So the key here that I'm showing, On the back end, we're converting GRIB data to ZAR using Xarray, and we're chunking that data up for fast performance. But to Mark's point, to the user, they have no idea about that. They don't need to know about that. The EDR API is just an abstraction layer away from the backend data store. They only really care about the coverage JSON output or the GRIB output or whatever output format the provider provides here. So that leads me to additional schema support. We've seen coverage JSON output so far. GRIB wouldn't be very interesting because it's binary. I don't have a GRIB reader on hand, but I did want to show, oh, wrong document open. I did want to show additional schema support. So one of our colleagues at the National Weather Service is an expert when it comes to iWixom. So we have terminal aerodrome forecast collections here. And this is just to demonstrate additional output formats that a provider can provide. So here you just have JSON output. Here we have text. So this is what a TAF looks like, a terminal aerodrome forecast looks like. It's used a lot in aviation. And then iWixom, this is the XML output in the form of iWixom. So in our implementation, luckily, we've been able to do volcanic ash advisories and tropical cyclone advisories too with this iWixom output. Let me move on now. So I wanted to give a couple quick client examples as well. This really kind of demonstrates how easy it is to create a client based on the EDR API, because the EDR API is structured API endpoints that are self-describing. So one of the ongoing themes you've seen today is that the API is rich in metadata, so you could dynamically create these clients. So this specific client is a METAR feature extraction for a point. So this list right here is dynamically created based on the collection metadata. So if I select air temperature for an ICAO ID, you'll see just with Plotly a line graph here for the METAR data. Now the cool thing here, if you keep an eye on the URL down here, this is the EDR API endpoint. And because it's so structured, like if I picked a different weather parameter, the only thing that changes is the parameter name. So if I search again, the only thing changing is the parameter name. If I change it to a different ICAO ID, the only thing that should change is the point here. So I think that's one of the key things there. You can rely on the API endpoints because they're structured, like you know what to expect. And because they're self-describing, you can easily create a dynamic client. So one more client to show here. So this is basically just to show that you can provide data from two disparate data sources because again, on the EDR API perspective, it's the abstraction layer. Like we don't care about the underlying data source. So this Canadian model data here, this originates in GRIB data. We convert it to ZAR using Xarray, and then it gets output to coverage JSON. So here you can see the output is just parsing the coverage JSON for the values here. This specific GFS data is actually coming from, I believe, the thread server. So you search again and the same data is coming up. It's being output in coverage JSON, and you really do not care about the data on the back end. All a user cares about is the data they see from the EDR API. So I think with that, I want to hand it off to Steve if Steve came back.
Yeah, no, I'm here, and I apologize for those of you who have contacts. I had a contact that actually folded over itself, so it was quite painful. So I had to step away to get that straightened out. Okay, and yeah, I think the only other thing I want to say is that you've often heard the term convenience APIs, and I think this really articulates the convenience nature of how EDR can be used, certainly. So Shane, I appreciate you stepping through all of these features. So some of the work that'll be coming up from the broader community is an extension of that metadata and search engine work that Shane started with, and that's going to be in conjunction with Tom Kralidis, who will be coming up next, and the API records group. So we want to very much utilize the API records approach and tie that to the MetOcean community. So that'll be some of the upcoming work that we'll be working on. So that's something to highlight. Thanks, Dave.
No, that's
Thanks a lot,
fantastic.
Dave.
Thanks for the demo. One quick question, Shane. How are you handling the lookup from your ICAO codes to the point value for the API?
Yeah, so that originally, Mark Burgoyne actually, glad Mark's on the call. Mark Burgoyne helped us originally when we were creating our clients here. And Mark can correct me if I'm wrong, but I believe it's just a relation, a mapping between the ICAO ID and a specific point. I don't know if that's in the form of a dictionary or JSON output. Mark may be able to elaborate if he remembers that original work.
It is a simple lookup table in the client itself. This particular example predates the work we did and one of the outcomes of actually developing this interface was the development of the locations endpoint, whereby you could have a named predetermined location as part of EDR. So we now have that capability, but this original demo predates that, so it translates everything into a position query.
Okay, so that makes sense. I was kind of asking a leading question there just to make the point that there's a distinction between a point query and a location query, where the location might just be an identified place without a point specified. So
yeah, and that location doesn't necessarily have to be just a position. It could be an area as well.
it's a monitoring site essentially, or a number of things. Sure.
Yes, it could be a catchment area, for instance, or sort of.
Right. Perfect. Thank you. We will turn this over to Tom, if you're there.
Great. Let me just share my screen share. Sorry about that.
We hear you, we see your screen, and we've got 20 minutes till we have to cut off. So go take it away.
Excellent. Thanks, Dave. So following on from the demonstrations from the previous presenters, you can see that the environmental data retrieval API as part of the evolving OGC API standards are really moving toward lowering the barrier to the data and extending the reach to the data and reaching out to not only the usual suspects, but possibly even information communities that we're not even aware of who can use the data because of this abstraction. So having said that, I probably should have mentioned that I'm Tom Kralidis and I work for the Meteorological Service of Canada, and our core activities are data dissemination in terms of geospatial web services. So we run a platform called MSC GeoMed, which gets 10 or 11 million hits a day through the current generation of OGC web services, and we are moving toward the evolving OGC API efforts, along with everybody else on this call and others in the community. So as a weather service, we currently produce 47 terabytes a day of data. Much of that data, some of that data gets out to the public, and we need to be able to disseminate it. So going back to Chris's presentation about we have all this big data. Well, we've been doing big data for quite a long time, all of us in the weather community, let's say. How do we sort of slice and dice and subset this data and make it meaningful and performant for users? So again, lowering the barrier to the data. So on the MSC side, we're an early adopter and contributor to the evolving OGC API standards, as well as an implementer of the emerging OGC API standards. We've implemented some of the other OGC API standards, such as features and processes. We're also working on the OGC API records effort, which I'll talk to a little bit about later. When it comes to EDR API, we are doing prototyping based on a baseline in Pygeoapi. So I should probably mention that Pygeoapi is a Python server implementation. It's free and it's open source, and there's a international community around it that from developers all over the world. It's been around for almost 3 years now, and the core goal is to implement all of the OGC APIs. And the EDR API is no exception. So we are looking at least I'm looking at here in MSc, of implementing core EDR support into Pygeoapi so that any user can download the tool and use it and be able to extend it to fit it into their own underlying data and so on and so forth. So I have this running on my local host here because there's a better chance it'll work, and I'm a firm believer of the law of the demo. So here's a landing page of Pygeoapi, which is essentially the OGC API specification. So if we wanted to list all of our collections, we can see here's all the collections that we have on this particular endpoint. So we have observations, large lakes. We have our global model, 15-kilometer model here that we do at MSc, plus a test data set that I've set up here for EDR. Of course, there's also, sorry if that's small, but there's also a JSON representation, as is the case for most endpoints and representations in the evolving OGC API standards. So coming back to lowering the barrier on the data, JSON as a sort of representation for moving data around through machines over the web is seems to be a good fit for purpose, and there's no exception here. So if we go down into the collection level for this EDR test, we see a number of different, we see title and abstract. I mean, I suppose the metadata should be better given that I'm working on the record stuff, but this is a demo. So there are a number of links, and a big thing about the OGC API standards in general are links and link relations, and being able to work with this concept called hypermedia, where you just click a link and something happens, and a lot less sort of machinery in between that. So these link relations, maybe they're a little bit better shown through here, but you can see we have a number of different link relations here, and some of these are core to the OGC API standards, but now we start to get into the EDR links, and we say this is a position query, and this is what you click for a position query. You can add additional arguments and query parameters as you've seen from the previous demonstrations, and you can ask for representations in JSON, in HTML. This is certainly extendable. EDR API doesn't prevent you, it allows you to output any kind of representation that you so choose. So if we go back to the HTML version of the page, let's click a position query for this actual EDR test data set, which is some UNV data that is coming from the NOAA, from NOAA's EDR API, for example. And here's some outputs based on that for wind speed and wind direction. So that is a basic implementation of EDR, and our plans in implementing EDR here at MSc are to we have a baseline in the Pygeoapi project in a branch which implements all of these endpoints, but we're here in MSc, we're currently working on a back end to all of our data to be able to provide, position, area, cube, trajectory, and so on and so forth. So we're almost there, and we're excited to be, part of this evolving work. Whatever code that we develop will obviously be made open source and made available to both the Pygeoapi community as well as other organizations who either want to use it or look at it and get some inspiration from it and do their own thing, what have you. So that's a sort of high-level view of where we are with EDR in terms of what our plans are in MSc, as well as putting it into off-the-shelf, free and open source software, which I think will be great for the spec in general. The other part that I wanted to touch on is we've seen numerous examples of straight up EDR request response design patterns. So I'm going to provide a demo here that basically allows us to use EDR outputs and do downstream things with them. So if I go back here, whoops. So this is the Swagger page or the OpenAPI representation in using Swagger. So all of the OGC API standards provide API documentation, and that is done using the OpenAPI specification. So this is a rendering of the OpenAPI document, or a get capabilities response on steroids, let's say, which is very, very user-friendly in comparison. It provides a number of endpoints. So we can look at any endpoint here. This is the landing page. And as a developer, I can look at it and say, okay, I can choose the format I want. I can choose the other parameters, and it tells you what it responds with for different error codes and so on. So let's try it out. If I click try it out, these these parameters come alive, and we click execute, and hey, it works. So as a developer, a web developer can sort of show up and use this query builder tool, if you will, to easily copy and paste, see what the design patterns are, and really fulfill and move forward that rapid application development that'll, again, lower the barrier to the data faster. So carrying on, I mean, here's all of our different collections in this specific endpoint. So let's get down to this EDR win calculator demo. So this is based on EDR API output from NOAA. So what we're doing here is we wrote a process in Python, which Pygeoapi is written in Python. So we wrote a process to take in the U and the V data and create wind speed and wind direction, calculate that wind speed and wind direction. So we can see here that here are the inputs, and this is, so what happens here, just let me back up and give an overview of the workflow. So the workflow here is that this is an OGC API processes endpoint. So what it will do, it's a custom process. You can define it the way you want. So what this particular process does in terms of a demonstration is a user provides the inputs. So basically the well-known text, geometry that they want to query, the temporal as well as the Z. So those three parameters are passed to this OGC API process, if you will. The process in behind the scenes does an EDR API query out to the NOAA server. The NOAA EDR API server responds with the payload, and then this process itself will do the wind speed calculation, and then it returns a response to the user. So there's a little bit of value add here that happens in terms of calculating the wind speed and direction. So here we can see the speed and the angle of the direction that came out, and this is all dynamically calculated. So the goal here, what I tried to demonstrate here, is the ability for these OGC APIs to work together, and the idea of pipelines or chaining between these OGC APIs. And you can use them sort of interchangeably and figure out what kind of workflows you want to apply or create yourself through OGC API processes, let's say, that can connect to EDR endpoints which are providing the environmental data. So I'll probably stop there with the actual demonstration. I'm just going to close out with some further words on what Steve and Shane mentioned around OGC API records. So we are looking at a strategy at bringing closer the EDR API as well as the OGC API records standard, and we're hoping this would turn into some sort of EDR or MetOcean based API records specification that allows us to do search with an EDR focus using the OGC API records specification. And I think I'm hoping that'll be a best practice, and it'll be used among various information communities. So just to close out, lowering the barrier, this revolutionary OGC API approach, and it builds on a lot of the good work that's been done by those who have presented previously, as well as the work in OGC in general. So I'm going to stop there and take a breath, and thank you all for listening.
Awesome. Thank you, Tom. in more ways than one. I think it's worth noting that most of the demonstrations that we saw were implemented on Pygeoapi, and I've done more than one presentation other than this meeting today that used Pygeoapi. It's the community is getting just so much mileage out of this piece of work, and it's great. Cool. Well, thank you. I will just pop up the agenda. There are a couple links on this agenda. So there's a link to the draft specification as well as the GitHub repository. And it's probably worth noting for those of you who aren't super familiar, all of the OGC API and the preponderance of OGC activities now are actually happening in GitHub, kind of out in the open. So the EDR specification has come together in 99 closed issues so far, and 61 closed pull requests. So if you want to go back and understand some of the design decisions that were made and see kind of how this all came together, you can, which is great. So here's the EDR, same for OGC API records that Tom was just talking about. And if you want to see the work in progress, kind of latest built draft, OGC has a drafts build of the specifications available at any given time, which is really nice. So the same thing is true of EDR here. You can see our kind of latest build, and anytime we merge a pull request, this will show up as a nightly build of the specification document. So with that, I will stop and see if anybody has questions.